Let's imagine the brain as a peach. On the cross section of that peach, we see the outer skin, the flesh, and the inner stone. The skin would be the newer part of the brain, the cerebral cortex, and then the fleshy part is the deep white matter, and the stone would represent subcortical below the cerebral cortex structures. Let's also consider the ways that we take in information in order to then produce behavior. Movement is a sort of behavior. We have vision, and when we subcategorize vision, we have clarity, eye movements, depth perception, and peripheral awareness. We have hearing, which is hearing a location of a sound, tones. Balance, we have head movements and body movements. We have taste and smell. Touch, so we have different sorts of receptors for and pathways for different sorts of touch. We have light touch, deep pressure, vibration, temperature, hot and cold, and pain. And then body position, taking in that information that is relating to posture and limb position. And then movement and breathing are also inputs. They're both inputs and outputs. We know about three main types of motor control. We have the spine and brainstem, the subcortical interior part of the brain, and then the cortical part of the brain. This is a slide from Z Health Education, which is a really wonderful training for the neurology of movement. So healthy, strong movement requires healthy, active neurological signaling, intact neurology. So if we have deficits in the cerebellum, the cortex, the PMRF, for example, movement, strength, balance, coordination, all of these things suffer. The brainstem is the part of the base of the brain that is connected to the spinal cord, controlling the flow of messages between the brain and the rest of the body, also controlling basic body functions, autonomic functions, breathing, swallowing, heart rate, blood pressure, consciousness, wakefulness or sleepiness. Then we have the spinal and brainstem motor control and the spinal reflexes. A spinal reflex is an automatic, involuntary neuromuscular action elicited by a stimulus. So the basic unit of a reflex is this reflex arc. The controlling center of the spinal reflex is located in one or more spinal cord segments. Deep tendon reflexes. Think of when the doctor hits your knee with a hammer and the knee spontaneously extends. We have primitive reflexes that are supposed to sort of fade away and as we grow older, but these are for eating and moving. They go away at certain developmental milestones. We have the vestibular reflexes. These are very important that we can actually train. So having to do with the eyes and ears and systems of balance, such as the righting reflex to keep the head upright and level with the horizon. And then we have the vestibulo-ocular reflex, for example, where the eyes go in the opposite direction as the head turns so that you see a stable image. And then we have pathologic reflexes. These are how doctors can assess the state and potential pathology or deterioration of the nervous system. These become present when somebody's nervous system has been compromised. For subcortical motor control, we're talking about intrinsic automatic movement, usually that you're not thinking about much. When we use subcortical motor control, we're receiving and integrating most of the input through what's called recurrent feedback loops. As movement teachers, this is something to be aware of, that a lot of the movement we are exhibiting is in this subcortical region. The output from these loops contributes to how big a response our body has to movement. Subcortical motor control, automatic, always occurring. Usually you don't have to pay attention to it. Our sense of equilibrium is composed of the vestibule in our inner ear and these three semicircular canals that are each at a right angle to one another, and they have this fluid, and they have hair cells and these little tiny organs with calcium crystals in them that all serve to detect different kinds of motion. So the semicircular canals each correspond to a different kind of head motion, and the little utricle and saccule also have to do with different directions of acceleration. What we're doing with this drill is working on the reflex that connects it to eye movement so that we can have a stable gaze. And if we're not able to stabilize our eyes, we're really not able to stabilize our whole body. I consider this to be a really foundational skill and something to really assess and work on. The semicircular canals detect angular acceleration to detect head rotation, and the otolith organs sense linear acceleration to detect both head translation and the position of the head relative to gravity. Basically, this is the reflex that helps you to stabilize the retinal image by rotating the eyes to compensate for movements of the head. An ideal VOR that tries to compensate for any arbitrary movement of the head in 3D space would generate eye rotations at the same speed as, but in the opposite direction to, head rotation. The subcortical structures are a diverse group of formations, neural formations, some of which you've heard of probably. Limbic system, the emotional center, the diencephalon, the pituitary gland, and the basal ganglia. These structures are involved in complex activities such as memory, emotion, pleasure, and hormone production. They act as information hubs of the nervous system as they relay and modulate information passing to different areas of the brain. So the limbic system, again, emotional and behavioral processes, motivation, long-term memory, olfaction. So our nose is connected, our sense of smell is connected directly to the brain because it's our most primitive sensory feedback. And then this area of the brainstem has a really long name, so we go by the acronym, but I'll say it one time, it's pontomedullary reticular formation, like the medulla. So PMRF, this is responsible for posture, global muscle tone, autonomic control. If we're able to target with certain movement drills the PMRF, we may be able to help folks who have pain on one side of the body or all their issues on one side of the body, because when working well, this area is supposed to be inhibiting pain on that one side, ipsilateral side of the body, and also inhibiting anterior muscles above T6 and posterior muscles below T6. So people in a lot of forward flexion would have anterior muscular tone that would not be properly inhibited. So that's why this is such a powerful area to just begin to learn about. So the basal ganglia and the cerebellum are the most prominent subcortical components of motor pathways. So technically the cerebellum is the hindbrain, and it is behind the cerebral hemispheres, behind the pons and medulla oblongata, and unlike other lobes, it's a distinctly separate structure. And the entirety of the cerebellum is detachable from the cerebral cortex in most brain models. It receives information from the sensory system, from the cerebral cortex, controls muscle reaction in relation to equilibrium, movement, and postures, controls coordinated movements, and the surface of it contains far more sulci and furrows than the cerebral cortex. The cerebellum integrates and simplifies complex data generated from all body systems, including cognition. So it's not just involved in motor control and output, but it's about coordination, coordinating complex movements ipsilaterally. So if somebody says they have terrible coordination or just kind of can't follow a rhythm or produce smooth movements or have much control over their movement. Somebody with a lot of control and very adept movement would have a very well-functioning cerebellum. So if somebody doesn't, you can actually do things to help um, stimulate that area of the brain. So coordinates movements, is in direct communication with the same side vestibular system. So that means the inner ear is intimately connected with all aspects of the cerebellum. It's getting a lot of information from that system. Another reason why that has so much bearing and impact on movement, and it directly stimulates the opposite side frontal lobe. The subcortical region takes in information and relays it to the cortex, where that information becomes analyzed, processed, interpreted. Language may start as just a collection of sound until it reaches the cortex and is interpreted into meaning. In the cerebral cortex, we have representation, both sensory and motor representation of the body, and this is called the homunculus, which means little man. And we have sensory, you can see here what is represented on the sensory map and the motor map, showing where in these images, where in the cortex it's interpreted and how much priority is given to certain regions of the body. So the hands, feet, and head are highly represented or generously represented. And this gives us some practical information in terms of cueing. So we can take advantage of what the brain is kind of most geared toward paying attention to. And where's the highest concentration of nerves? Where's the most efficient way, and given that, to draw awareness to? Paying attention to internal sensory information, your brain can map a better homunculus. This improved representation gives the brain a better reference point from which it can select the optimal motor strategy for a task. If this map becomes unclear due to injury, underuse, scars, pain, this is also referred to as cortical smudging. I wanted to look at common yoga cueing, and I drew from examples from 3 different books, teachers, years. So this is from Baron Baptiste's book published in 2003, and it's Triangle Pose. And these are all examples of internal verbal cues. I suppose drop your lower rib cage toward the floor might be a bit of an external cue because it has an external marker there toward the floor. But for the most part, internal cues. So we have heels in one line. So he says for triangle, heels are in one line, maintain strong action through the legs, spiral your inner thighs outward from one another. And I find that always rather vague. The spiraling can be elusive, I'm sure. Scoop the tailbone down and under, not sure why. Radiate through both arms, keep upper hand active. Lift the pit of the belly inward to lengthen the spine. Drop lower rib cage toward the floor. Twist the torso, stacking upper over lower lung. Draw scapulae down toward the hips and gaze high toward the upper thumbnail. So this is really, really common, and this could be challenging for a lot of people without much awareness of these aspects of their body. And this is from Mark Stevens' book published in 2010 for Triangle. Start with the feet separated the length of one leg, turn the right foot out 90 degrees, left slightly in, shift hips to left pressing right sitting bone toward left while reaching out to the right toward the spine and the arm to the point of maximum extension, then release the hand onto the lower leg or ankle. Offer the option of looking down to make it easier on the neck. So verbal internal cues. This would focus on body processes and internal systems like muscles, kinematics, pressure, and more. This would be an example of an internal verbal cue. Person in this pose being told to roll shoulders back, broaden and lift the chest, press the feet down, press down with the feet, squeeze the ankles toward each other, lift the hips off the floor toward the ceiling. That's a little bit of an external cue. Let your head drop back. Really common sorts of cueing in yoga. This is an article by a fairly well-known biomechanist yoga teacher named Robin Capobianco, who did a lot of studies of cueing and how it altered different sort of verbal internal cueing and how it altered the body. And she's asking here, are muscular engagement cues doing more harm than good? So in terms of activating what she's calling proper muscular engagement. And next slide is a example of 3 different kinds of cueing in bridge pose and how they create different outcomes in terms of percentage of engagement. For people in chronic pain, it can be difficult to shift the attention away from the painful area, and then that can be a vicious cycle and a loop whereby that area becomes more better mapped, actually. So we can help create internal cues for other areas of the body, focusing away, distracting from the pain, but also helping to rewire for more pain-free movement connections, which is a great thing for anyone in pain. And then internal cues, theoretically, maybe not for everyone in every situation, but could improve body awareness through attention. We can help our students become more somatically aware, listening to themselves, paying attention to internal sensations. Interoception is involved in many different physiological systems like the cardiorespiratory, gastrointestinal, nociceptive or threat or pain system, endocrine and immune systems. So internal cues can conceivably help to refine interoception. It is a misunderstanding that more interoception is just better for everyone. Sometimes it's really just about a mismatch or clarifying interoception, calibrating it to function better. Someone with trauma might have extra interoception regarding one system of the body, or just a dysregulated interoception. So again, I think it's good to have different sorts of cueing and not just internal cueing. Interoception is contemporarily defined as the sense of the internal state of the body, both conscious and non-conscious. It encompasses the brain's process of integrating signals relayed from the body into specific subregions like the brainstem, thalamus, insula, somatosensory, and something called the anterior cingulate cortex, allowing for a nuanced representation of the physiological state of the body. These signals are projected to the brain via a diversity of neural pathways that allow for sensory processing and prediction of internal bodily states. So it would make sense that there would be a disconnection or a misrepresentation between body signals and interpretation for some disorders such as anxiety, depression, panic disorder, eating disorders, PTSD, OCD. So again, that's why more isn't necessarily better. It's just it's that we're after more functional, better matching, better integrated interoception. What you want to do is not switch to the far or near until you have clarity. So you're going to find your near point and focus on it as close as you can with clarity. And then I'm just going to show you with my thumb out at arm length. So I would look at focus, and then focus on my far point, focus on near, focus on far. So I'm toggling between convergence and divergence. And you might notice a little lag time. So near, far, far. And I'll just show you with a longer distance away. So I'll get close so you can see my eyes. I just came in from the cold, so my eyes are watery, my nose is red. so I really feel that motion and that movement in the eyes. So that's two things, convergence and near far. I'm going to do a little time-lapse video of the sequence of the progression of regressing or progressing the challenge level by position. So any kind of eye exercising can be quite fatiguing to the muscles. So this is a little sequence of a kind of reset and eye massage. So massaging around the eyes, kind of where the extraocular muscles come from, the outer corners of the eyes, right below the center, and the inner corners of the eyes. And then I do strokes across the under the brows, kind of with a little bit of pressure from inner to outer corners. And you can circle around the eyes or do little figure eights, 2 or 4 fingers. And then I often have people, if I'm doing any kind of eye training, vision training, I will always do this, especially, I always do this in classes actually. And then palming, I'm going to show you in a minute, where we just basically seal off all light, palming, seal off all the light, and just relax the eyes. So, and you can, if you're sitting at a desk, put your, or table, put your elbows down on the table and just rest the head and relax the eyes. This is by James Karim, PhD from the Department of Neuroscience at Johns Hopkins. Cerebellum, Latin translation is little brain. It only accounts for 10% of the brain's volume. It contains over 50% of the total number of neurons, which is really interesting. It's been considered historically a motor structure because damage to it manifests as and looks like poor motor control and posture, but there's more to it. The major functions of the cerebellum are maintenance of balance and posture, so it's important for making postural adjustments in order to maintain balance. It gets input from the vestibular receptors and proprioceptors, so it modulates commands to motor neurons to compensate for shifts in body position or changes in load upon muscles. And then it also is responsible for coordination of voluntary movements. Most movements are composed of a number of different muscle groups acting together in a temporally coordinated fashion. So one major function of the cerebellum is to coordinate the timing and force of these different muscle groups to produce fluid limb or body movements. Rate, rhythm, force, and accuracy are really the big jobs. Cerebellum is really important for motor learning. It plays a major role in adapting and fine-tuning motor programs to make accurate movements through trial and error process, like learning to hit a baseball. And then cognitive functions. Although the cerebellum is most understood in terms of its contributions to motor control, it is also involved in certain cognitive functions such as language, like the basal ganglia, which the cerebellum is historically considered as part of the motor system, but its functions extend beyond motor controls. The cerebellum kind of fine-tunes the coordination of movements produced elsewhere in the brain and integrates all of these things to produce fluid movements. It also plays a role in analyzing visual signals and vestibular, so there's a lot of overlap, of course, and integration. This is another quote from McGill University, and I love this because it just reiterates what we've been talking about. The operation of each hierarchical level in the motor control system is extremely dependent on the sensory information that it receives. Any voluntary movement can be described as an intentional effort undertaken jointly by the motor cortex and then numerous other neural systems acting in a consulting capacity. So first at the top we have the objectives of movement that we were talking about, the frontal cortex receiving information from a large number of axons projecting from the parietal cortex, understanding where your body is in space, spatial perception, analyzing the position of the body and its various members in space. Then we have secondary motor areas working with the cerebellum to specify the precise sequence of contractions of various muscles and tissues required to carry out the selected task. And then we have the primary motor cortex and the brainstem and the spinal cord, which all come into play to produce the contractions of all of the muscles and tissues needed for the chosen movement. So the primary motor cortex determines how much force each muscle must exert and then sends that information to the spinal motor neurons and interneurons that generate the movement itself, and as well as postural adjustments. We have sensory information that comes in and enters into the spinal cord, goes up and travels into the brainstem, goes through the relay station of the thalamus, and then up into the cerebral cortex. And then that goes, distributes out, disseminates back down to the cerebellum, which is kind of coordinating and checking and correcting the basal ganglion. That both of those going back to the thalamus because that's the relay center, back to the brainstem, back to the spinal cord, and producing motor output through movement. So looking at the brain and the neural functioning started to finally answer some questions in terms of like, well, why does someone learn this and not that, and why are they in pain? Why can't they access this movement? Why are they uncoordinated? Why are they slow or fast, or something going on this side or that side? Just all of the questions you would have looking at somebody's movement capacity and movement output. So I think looking at this structure can be incredibly helpful, this information.
I'm going to show you a cerebellum assessment that I do with almost all of my clients and students. And then I'm going to show you two coordination games. I think they're really fun that you can incorporate into your own training, into personal training, and even into group classes. So here's a cerebellum assessment. So we're going to be doing rapid supination, pronation of the hand. So whichever side is less coordinated or slower, that would be the side that would need some more input. Usually complex movement. If you're only doing linear movement in your practice, you're not really requiring much of the cerebellum. When you're doing more complex tasks and complex shapes, you are. So here would be my cerebellum assessment. Here's one of them. So taking one hand, switching between hand down and palm down, back of hand and palm, as quickly and as accurately as I can. So it looks like this. Okay, that would be my right side, and then I would assess my left side. It's going to be slower. It starts to break down and deteriorate after a while. You don't want to do that. That's kind of cheating, where you're keeping the edge of your hand. You definitely want to be lifting it. See, now I'm breaking down already. Lifting it up off of. Okay, so that's the upper body. The lower body, you can do a foot tap. So a rapid Again, as fast and accurately as you can, foot tap. Okay, so you're seeing if people are really slow or really choppy. So my assessment today is going to be my left cerebellum, my left hand, definitely less coordinated. But interestingly, my right foot is less coordinated.